Welcome to RF transceiver design course. We are discussing about mixer design and we are in the discussion of the noise in the mixer. So, for passive circuit we have seen. Now we will see for the active components, active mixer. So, flicker noise analysis in active mixer. Now one of the important noise that we need to consider in active mixer is a flicker noise, because our frequency is down converted to 0 and that flicker noise is also going to affect the entire receiver performance. So in order to analyze the flicker noise, we will have a here Vn voltage, which is denoted as a low frequency noise Vn, and we are considering only the single transistor noise, and then we can multiply with the 4 times, and each transistor is getting a current I, which is a DC current I, because we are interested to consider the switch. Switch is going to add this noise, and that is why this portion we have considered it as a constant current I, and same constant current I is also flowing through the transistor M5 and M6 and M3 and M4. So if you consider if you have a input which is a sine omega LOT, then your overdrive voltage IOD, and if it is a full swing, you will have a current I, maximum current I, and uh, I in the positive direction and minus I in the negative. So because here it is a sin omega LOT that we have applied, and here it is a minus a sin omega LOT. Now if we want to consider, so this is a noise which is Vn is appearing at the M3 transistor. It can we can consider the same thing for other transistor also. Now this is a complete LO signal which is applied to the, and Vn which is overimposed on the LO which is provided here. Now what will happen that during the zero crossing, when LO is a zero crossing, at that time this noise will have a very high amplitude pulse, and that is equivalent to current 2I. So if you see that, if you can observe that if we try to uh, zoom this portion, then here the slope of this portion is given by S, which is equal to Vn by delta t. So this is a small duration delta t, during which we can consider that we will get the complete pulse of the DC, which is current 2I. Now the width of this pulse, which is a delta t, is depend upon that how much noise voltage is there. So you can see here that as the noise voltage is high, this delta t is high, and it will have a different, the current 2I is going to remain constant, that is the amplitude is going to remain constant, but its width is going to change. So if we are interested to find the on current I on, which is equal to 2 by T, that is a time period T, this because if you see this is a twice of the omega LO. So 2 by T into current 2I, that is amplitude, and that is appearing at the time duration of the delta T. So on current, this is the average output value, so average current ION, and now here this delta T we can replace with 2 by T into 2I into V n by S. So, we can write it down this equation as a 4 I into V n by S cross T. So, this S here we can also get because there is a this amplitude based on the amplitude of the sign, that is A sin omega L O t, we can get S which is equal to 2A into omega L O, and the T is given by 2 pi by. So, this T here is a time period of this T, this is a T by 2. So, this is a T between 2 pulse. So, this T is given by 2 pi by omega L O. When we put this 2 in this equation, we will get I on current, which is I pi A into V n. So, this is very important equation, and we can get many information out of this. One is your noise current is depend upon the amplitude A sin omega L O t. So, it is inversely proportional to A sin omega L O t. So, whatever A amplitude of the square wave, if we can have a higher amplitude, we can reduce this I on current, and it is also proportional to the current I. So, what is the current I? That is flowing into the your mixer. So, this is on current, I on current, average current. Now, what will happen if we consider the complete spectrum? So, if we consider the complete spectrum, then this delta t, this delta t by t is much less than 1. So, if we consider the complete spectrum, entire spectrum, this will be narrowed down, and then we can consider this as a train of impulses, and its impulse duration is 2 by 2, and that we can consider for finding out the on current. Now, if we consider the offset voltage V offset in order to have the analysis of the active mixer, then what will happen, that in offset voltage consideration, the amplitude, your delta t is equal to V offset by S, and your amplitude is going to change according to the your noise current. So, in this case what is happening, that we will consider GMI into VNI, that is a transconductance is multiplied with the voltage VNI, and we will get this I on average current. So, I on current is equal to 4 I into V offset by S cross T. So, here we can write it down this as a current I is given by GM into VNI, noise voltage, and this is V offset by S cross T. Now, GM transconductance can be written as a I by V. So, we can write I by GM transconductance I by V effective into VNI into V offset by S cross T. So, what we will get is a S cross T, we already know from the last equation S and T, if you multiply, what you will get is a 4 into pi a, the omega LO will be cancelled out. So, 4 I divided by V effective into VNI, V offset. So, this 4 will be cancelled out, you will get a I by pi a VNI, V offset by V effective. If you see that your on current is depend upon the offset voltage as well as the voltage V effective, that is related to the transconductance GM. So, here your flicker noise is also considered as a dependent on the offset voltage, and that can be reduced in order to reduce the flicker noise. So, here how this flicker noise is uh, considered in order to uh, solve the problem of the active mixer noise. Now, the one of the way by which we can improve the flicker noise is reducing the current, because this effective current I passing through the switch. Now, how can we reduce this current, effective current which is passing through the I? Because if this current is reduced I, then what will happen? Your transconductance GM is reduced, and if this transconductance GM will reduce, your gain is equal to 2 by pi GM into RD. If there is a load RD is there, then your this is your gain conversion gain. So, your GM will also, your conversion gain is also reduced. So, in order to reduce the noise, you are reducing the conversion gain, but that is not the way we can reduce the, because here we have only considered the flicker noise. If we consider the thermal noise and white noise, that in the thermal noise what will happen, that gain is in denominator, and if you reduce the gain, your noise will increase. So, what is the solution? One of the solution is that you reduce the amount of current flowing through the switch, but you give some additional current to the uh, transistor, that is the input transistor, which is going to convert a GM into RF. So, that is one of the way by which you can increase the you can reduce the flicker noise and improve the, means keep the gain constant. So, this is one of the way by which we can have a better noise performance. There are many papers or research article you can find out in which they have considered to increase this tail current and reduce this current flowing through the switch and improve the flicker noise. Now, if we consider the thermal noise, so flicker noise, we also need to consider there is a load also. So, in in the load, what will happen, noise in the output load section is a critical, and it is especially in mixer as it does not undergo frequency translation, and it will directly come at the output. So, what is the reduction strategies for load noise? If there is a RL resistance is there, it is directly going to contribute. But one of the way we can reduce the noise is by using the PMOS active load. So, when a PMOS active load is employed, the device channel length should be carefully chosen to ensure that 1 by f noise corner frequency is below the frequency of interest. and this prevents the excessive noise at the output. So, one of the reduction strategy is to use the PMOS active load. Another strategy that you can use a polysilicon resistor, which will not add that much noise, and we can reduce the effect of the flicker noise. Third is a, we can also use a means in the input FET noise. So, noise in the low transconductance FET is present alongside the RF input signal and undergoes a frequency translation. So, just like a RF signal, it will also get the frequency translation whatever there in the FET noise. So, while considering the load, design of the load, we should also need to make sure that the whatever component, active component that we are using at the load should be carefully chosen. Flicker noise up conversion. So, flicker noise in this FETs gets up converted to the LO frequency and other odd harmonics during the frequency translation process. So, we while considering the flicker noise in up conversion, uh, what will happen that it will add this FETs get up converted to flicker noise in this FETs gets up converted to the LO frequency and other harmonics during the frequency translation process. White noise translation, white noise at LO, omega LO and other odd harmonics is translated to the DC during this process. And what is the impact, because we are using a 0 IF, if we directly convert into the 0 IF. So, when the output frequency of entrace lies at or around a 0 intermediate frequency, the transconductance FETs primarily contribute white noise after frequency translation, and this is because the flicker corner of these devices is usually much lower than the LO frequency. So, that also needs to be considered while designing the mixer. Now, we will see the active mixer white noise, because initially we have considered the flicker noise, now we will try to consider the white noise. So, in order to check the in order to find out the white noise, there is a three components. One is a contribution of white noise, there is a three component. One is a switch, due to the switch, then another is due to the input FETs, and then third is a load. So, what will happen, most of the time when both the switch are on, that will contribute the noise, and we also can find out when there is a switching is happening, how the input noise is switched and considered at the output, and at the load directly, because there is a two loads. So, load directly you can consider the direct load resistance RL, that is 4 kT by RL, and it is multiplied by 2 because there are two resistance. So, here mixer is loaded with a resistance RL and the current conversion gain is 2 pi by Gm, and so noise figure we can directly write with respect to Rs. So, as we have already discussed multiple times, this is a 1 plus then all the noise that is at the output divided by the Gm into here what is considered is a current conversion gain. So, that is a 2 by pi into Gm, and if we consider current conversion gain, then we are dividing by 2 by pi into Gm, because these all are a current quantity. So, now we will see that how this term I by pi A came. So, here what will happen that, so there is a LO square wave, and this LO square wave, this is a LO signal and this is a time t. So, what will happen that there is a the noise here, the way we have considered the in the flicker noise case, similarly there is a noise pulse train which is generated at the zero crossing, and that noise current IONT is equal to PT into VNT. So, this PT is a pulse train which is a this is a PT and the time period, this is a T by 2. So, in all the analysis what we have considered, we have considered the stationary noise, but when we use a case for the switching, means because noise here is a switching. So, that is a we need to consider a cyclostationary effect, and if you consider that and if we find the average spectral noise spectral density for ION, we can write it down 4 kT gamma, and now GM is a sample because the transconductance, that is 1 by T into T. So, if we want to consider the sample dt, so if we consider the T by 2 period of time, it can be written as 8 kT gamma by T into the integration with respect to T by 2, and this we can write del IO by del VLO, that is a GM effective GM when we consider the del IO by del VLO into dt, which is equal to 8 kT gamma by T by 2 del IO, we can write del IO by del T and del VLO by del T into dt. So, we already know that del IO by del T, we can write it down because it is a pulse train, we can write it down 2 into I into delta T. The amplitude is a 2I of this pulse into delta T, and we can get del VLO by delta T, which is a slope. So, as we have considered in the last slide that this is a slope and that del VLO by del T is given by S cross T. So, what we will get is a if we try to find out 4 kT gamma into 4I by S cross T, and S cross T is nothing but we already have considered, that is a 4 into, so 4 kT gamma I into pi a. So, this is what is considered for the FET switch noise, that is in the SION 4 kT gamma GM switch, and this is how 4 kT gamma I by pi a can be written, and this is a load current. And when we try to find out a noise figure, we will 1 plus entire current by the current gain into RS, that is a source resistance RS noise. So, this is how we can find out the white noise for active mixer. Now, we will try to consider the linearity of active mixer. So, if we consider the second order nonlinearity, so the potential contributor for second order distortion in this uh, mixer is a input affinities, switches and a feed through. So, that will if there is a feed through, it will add a more non-linearity, because that will add the components which will generate the non-linearity in the system. So, in this case also, if we try to consider the pulse train which is mentioned here, and here this is a active mixer configuration. Now, in this configuration, this current I O plus Gm V in, which is flowing through V in, this is a V in voltage, and now if some portion of V in, which is called alpha V in, because we need to consider the feed through, and what if there is a feed through due to the capacitance here at high frequency, and that feed through has a portion alpha into V in. Here alpha is much less than 1. So, that portion will come at the input side, and similarly at the here it is a minus alpha into V in. So, that will also be switched, and we will get a pulse train like what we have considered in the noise case. So, we can write a 2I if effective transconductance because always this is not a complete switch, and it is going to be on at some period of time, both will be on, and we will get a GM effective which is equal to 2I by delta V. This is a 2I current equal to 2, if you write a current I, delta V current I, which is a I naught plus Gm into V in, and here your output current I O, if it is Gm effective into V in, then what we will get is a, this is Gm effective, your V in is 2 alpha into V in, that is because there are alpha V in on this side and minus alpha. If we consider the differential, it is a 2 alpha into V in, which is given by 2 in divided by, so 2 divided by delta V I naught plus Gm into 2 alpha V in. So, if we consider here the second order, so as we have solved, if we consider the second order point, so second order is given by a 4 alpha into delta V Gm 2 Ts by T. So, this will be on for the period of the 2 Ts by T. So, we also need to multiply it with the, because we are considering the average, and it is only this it both will, this feeds will on at only this period of time, and for considering that we are multiplying it with a 2 Ts by T. So, the total A2 is given by 8 alpha into S cross T into Gm, and your IIP2 we can write it down A1 by A2, which is S into, your A1 is nothing but 2 pi by that is a fundamental constant, that is a 2 by pi into Gm. So, that if we if we consider the A1 as a fundamental 2 pi by gm, and then this 8 alpha into S cross T, what we will get is a S into T by 4 pi into alpha. So, what it says that this alpha is important here, this coefficient alpha, and if we have a less feed through alpha, we can have a better IIP2 performance, because the amount of feed through if we can reduce, then we can able to improve the linearity of the mixer. And for input FET second order nonlinearity, so in that case we have considered the switch for input FET second order linearity. The second order component is given by 1 half beta V in square, and second order coefficient we can calculate the same 2 beta V offset by S into T. So, you will get IIP2 which is V effective S cross T by pi. So, the switches contribute mainly due to the parasitic capacitance at their common source and in presence of a mismatch. So, their contribution is dominant only at high frequency and can be improved by reducing the parasitic capacitance at common source of each pair. So, if we try to reduce the parasitic capacitance and feed through, then we can able to improve the linearity. So, this is how for considering the noise and linearity, how we can improve the performance. We will discuss more about the other mixer architecture in the next class. Thank you.